Today we're going to be talking about trigonometric functions and radian, which is what we're going to be dealing with in this class. So a radian measure of an angle at the center of a circle is the length of the arc that cuts the angle from the unit circle. Basically what that means is if this unit of our circle is 1 and the length along the arc is also 1, then this angle here is 1 radian. Okay, so that's 1 radian. That's bigger than 1 degree. There's a key formula we need to remember. The arc length S of any arc is the radius of our circle times theta. Now the key thing you need to remember is R has to be in radians. And everything that we are going to deal with in this class is going to be in radians. So keep that in mind. Okay, find the length of an arc subtended on a circle of radius 5 centimeters and a central angle of 123. So remember the formula I just gave us. S equals R theta. So length of an arc, that's what I'm looking for. The radius of our circle is 5, 123 degrees, but remember theta needs to be in radians, so I convert it by multiplying by pi over 180. Now when I plug that in my calculator, we have 10.734. Also realize we're always going to be rounding the 3 decimal places in this class, so I'm going to be looking for 3 decimal places on all problems. Okay, review of basic trigonometric functions. So an angle measure theta is placed in standard position at the center of the circle. So here's theta. And we have our terminal side ending at some point xy. The sign of the function, remember, is going to be y over r, or opposite over hypotenuse. Cosecant's the reciprocal of that function. Cosine is x over r. Secant is the reciprocal of cosine. And tangent is y over x. Cotangent is going to be x over y. So that's just a real quick review. Also a real quick review of graphs. So graphs of our functions. So remember cosine starts, I remember this as cosine starting up at its amplitude and going through one rotation, remembering that its period is 2 pi. Sine starts at the origin, goes through one rotation, and it ends its period at 2 pi. Tangent, now, tangent has asymptotes starting at plus or minus 2 pi, because that's where our function is undefined, and the distance between our asymptotes, or the period now, is different, and that's going to be pi. Secant is basically just the reciprocal of cosine. So what I usually do is I usually put asymptotes down wherever I see zeros for cosine. So that's where my asymptotes were for secant, and then it's just the reciprocal. So it's just the u's going up and down. Same thing for cosecant. Cotangent, you start at 0, end at pi, so its period is also pi. That's where my asymptotes are. And it looks like the opposite of a tangent function. Now the even functions, remember even means I'm symmetric across the y-axis. Which functions look like they're symmetric across the y-axis? That's y equals cosine x and y equals secant of x. Now remember, last year you probably learned some even-odd properties having to do with identities. Remember that means that the cosine of negative x is equal to the cosine of x. So that means that our function is even. And the same thing is true for secant. Now all the other ones are odd functions. y equals sine of x, y equals the cosecant of x, y equals the tangent of x, and y equals the cotangent of x. And remember, our odd property means the negative of the function is going to equal the sine of negative x. So that's why that property is also true. And it's true for all of these other trigonometric functions, tangent, cotangent, and cosecant. Quick review of graphing trigonometric functions. Remember, A gives us our amplitude. D gives us our vertical shift up or down, exactly what it looks like. Factor out the B, that gets you your period change, and then the horizontal shift of C. Graphing that function, stating the domain, period, and range. I'm also going to state a few other things that help me graph it. So my period, remember, is 2 pi over 4, which simplifies 2 pi over 2. Our phase shift is pi over 4 to the left. So what I do, because it's sine and sine starts at the origin, I first put my negative pi over 4 down. Now I go through and I add pi over 2 to that. So if I add pi over 2, that's going to get me 2 positive pi over 4. I start one period there, end one period there. Now if I add another pi over 2, I get 3 pi over 4. Now remember, sine starts at the origin. Halfway in between I have a 0. Halfway in between I have a 0. My amplitude is 2, so I go up and down to positive 2 and negative 2, so that's going to help me with my domain and range. But the negative means I start by going down. So halfway in between the zeros, I'm down at my amplitude. Halfway in between the zeros, up at the amplitude. And I go through that same periodic relationship. Now, they want me to find the period. The domain is all real numbers. I can plug in positives, negatives, and such. Our range is my highest is positive 2, my lowest is negative 2, and we're inclusive, so we are going from negative 2 to 2 for our range. Now notice one thing about this function. For our test to determine whether or not this is 1-to-1, we would draw a horizontal line. Notice how our horizontal line intersects at more than one point. It's going to actually intersect at an infinite amount of points, because remember, this graph keeps going up and down forever and ever and ever. So the reason I talk about that is because we also have to remember inverse trig functions. So as I was just saying, none of these 6 basic trig functions are 1-to-1. And this figure is the figure that I had earlier in the PowerPoint. These functions thus do not have inverses. That's why I have to restrict our range for our inverse functions. The key ones you guys really need to remember are these top 3, but I want you to write all of them down. But those are the key ones that you need to remember. Now keep in mind that your range for cosine, for inverse cosine, remember inverse cosine, It's kind of like Jeopardy. So at what angle Y does the cosine have the ratio of x? So we give you the ratio. You now need to give me the angle. So for the range, the angles that you're going to be looking at are quadrants 1 and 2. For both inverse sine and inverse tangent, you're looking at quadrants 1 and 4. But notice how in these quadrants, you're looking at the negative angles. Again, the reason for that, let me get a really quick graph of a sine graph in here. This point right here would be at negative pi over 2. That point right there is positive pi over 2. If I just look at this blue highlighted area, then I know that those points, all those points, and I ignore everything else on our graph, now that function's 1 to 1. Well, remember, this value over here, well, that was at negative pi over 4. I'm sorry, pi over 2. This value there was at positive pi over 2. So that's why we restrict our domain. Okay, first example is you need to make sure that your calculator, because you're going to need your calculator. It's impossible to do these without a calculator. Is in radian mode. So make sure, check the mode on your calculator right now. Make sure it's in radian mode. And you do the inverse cosine of 0.4. Remember, to get that inverse cosine, you do second cosine, not 1 over cosine. Okay, so when you get that in your calculator in radian mode, we get 1.159. Now, I need that angle now. This angle right here is in quadrant 1 because our calculator knows our domain restrictions. So the calculator is just giving us this angle right there, which is 1.59. Well, we know from our unit circle, cosine's also positive in quadrant 4. So there's a point where the cosine is also 0.4 in quadrant 4. So what we need to find is we need to rotate all the way around to get to that angle. What your calculator gives you is it gives you essentially the reference angle. So it's giving you from the x-axis up to that point. So it's also giving you 1.159. It should be 1.159. I just wrote it wrong. It's giving you that angle that's rotating down. Okay, so what you need to remember is you're going to do 2 pi minus 1.159 to get your correct answer, and that is 5.124. Again, 3 decimal places. Make sure you're rounding to 3 decimal places. Our next example, solve for x on the interval. Now notice how I didn't have any restrictions. So we're going to have to incorporate all of our rotations. Remember that the period for tangent is equal to pi. So we do inverse tangent in our calculator. Inverse tangent of negative 3. And I get negative 1.249. So my answer is that number plus all possible rotations. Plus all possible rotations. Since my period is pi. It repeats every pi. But k now, I need to add in k because it's going to keep rotating around our unit circle. So therefore, you have to tell me that k is equal to integers. But now we know what x equals. Okay, our next example. Notice a few things. These are all non-calculator questions, and you're going to give me your answer in radians, because in calculus, we are rad. So, inverse sine. Where is the inverse sine equal to negative 1/2? Remember, we're just looking in quadrants 1 and 4. Those are the two quadrants we're looking for inverse sine. Well, sine is positive in quadrant 1. It's negative in quadrant 4. So you have to look at the angles in quadrant 4 from our unit circle. And that's negative pi over 6. Now, again, remember, I didn't choose 11 pi over 6 because of our domain restrictions. Our domain restriction was negative pi over 2 to pi over 2. Inverse tangent now. Inverse tangent. Inverse tangent, where is the tangent equal to 1? From your unit circle, that's pi over 4. And lastly, where's the cosine? Negative root 3 over 2. Again, that's the challenging one. For cosine, we're looking in quadrants 1 and 2. Cosine is positive in quadrant 1, but negative in quadrant 2. So you have to look at your angles in quadrant 2. Where is the cosine equal to negative root 3 over 2? That's going to be 5 pi over 6. And for each one of these, because our functions are 1 to 1, notice how I have one output for every input. One. It's 1 to 1, so one output for every input. That's it for today. Please make sure you submit the video summary on time.